Hello, welcome to our next set of stat notes. We are now on sections 6.3 and 6.4. These two get combined for one homework assignment, so that's what we're covering this next section. We're kind of making an important transition now. We're starting this transition. So far, the statistics we covered probability, we covered kind of the idea of what statistics is, and we covered a lot about after you've collected your data, your sample data, how to calculate like the mean, the median, the mode, the statistics. Remember those terms. But a big part of statistics is after you've collected your sample and you've calculated those measures of it, like the measures of center, measures of variation, then taking that sample value, the sample data, and making some kind of logical conclusion or understanding statement about the entire population. Usually that's kind of the big goal of statistics, is to take a survey or collect some sample data from a small portion of the entire group and then try and use that to say things about the entire group. That's what we call inferential statistics. So, so far we studied sampling, descriptive statistics, where you find mean, median, mode, probability. Talked about the normal distribution in the last couple of sections. But now we're going to integrate all those things. We're going to put it all together and learn about inferential statistics. So to make inferences, we take a sample, compute things like the proportion, the mean, or the variance. So those are kind of different types of statistics you can calculate. And then use those statistics. Remember, statistics is just named for measurements we calculate on a sample set of data, not on the entire population. So we take the sample data results and we make inferences, conclusions about the population's parameters. Remember, parameters are the values for the entire group. So I take a sample of my students at Black Hills State grades. Well, I just take a sample and I say, okay, the average grade is blah. Then I go and I say, okay, based on that sample data and that average grade I got for that sample, I can kind of make a guess or an estimate about what this average grade would be for all the Black Hills State students, or all of my students, or something like that, the bigger population. That's the idea. So to make inferences, the big thing is we're going to take sample, we can compute values like the proportion, mean, or variance, because that's usually what we'll make inferences about, and then make an inference about the population. So we use the statistics to make inferences about the population. That's the goal. That's where we want to get to. Now, before we can do that, we have to make some kind of statements, some conclusions about how the sample results relate to the population results. There are certain type of measurements you could do with a sample that don't really give you very good understanding about the entire population. A really good example of this would be like the range. So range, remember, you just take the top, bottom minus the top number minus the bottom number, and you get that range, the spread. Well, if I take a sample, if I don't get a very high number at my sample's range is going to be really small because it doesn't include the really high number that's possible for this set of data. Or if I didn't get a very low number in my sample, I'd get another small range. So it's really easy to pick a sample that's not going to have a very valid range. It's not going to be close to the range for the entire population. So range, we'll find out, is not a very good thing to measure with sample data. We usually don't try and figure out the range for the entire population. I'm not going to go out there and look at the heights of all high school boys and say, well, I took a sample and I said the range of values was like 50 inches between the top and the bottom. But then I find out, if I go look at the whole population, it's even way bigger than that. Like that was actually really small. The 50 inches is kind of big. That was a bad example, but that's the idea. Some values this isn't very good for. Some it is. The idea is we'll take a sample, try and understand that sample by calculating values like the mean and the standard deviation, proportion, variance, all these different things, and they'll compare that and kind of try and figure out things about the whole group. So, for example, mean is a good example. It's one we work with a lot. So means are average of all samples of a given size. So if you take like all the samples of size 5, that means like every group of 5 students you could pick out of all the different students you're working with, the whole population. And then we find the mean of that sample. We call that a sample mean. So sample mean is the mean of a sample mean. They have a nice normal distribution. So if I look at all the different like samples of size 5, I could pull out of my group of students and put those all on a chart. They would actually make a nice normal distribution, this nice bell-shaped curve, all the different sample means, sample averages. So I'm looking at every group of 5 students I could pick out of my entire population and putting those on a chart and finding out that they have a nice normal distribution. And then that they target the population mean. What this means when they say the target the population mean is that the average of those sample means is going to be the same value as the population's average or the population's mean. They target the population mean, which means the average of all the samples is the population mean. So if I look at my sample means, these are all little different sample means I calculate and make my distribution. Well, the average value, the value right in the middle, that is going to be the exact same value as the population mean. So the average of all these different sample means is going to be the population's average. What this means for us is that you can actually expect, when you collect a sample set of data, that the average from that sample, the little sample mean, x bar, is going to be somewhere close to the actual mean for the entire group. Some of them are further off, but we know with these normal distributions that the values at the ends are very less likely. The majority of the values are in the middle. So another way of thinking of this is saying that when you collect sample data with regards to mean, the average of your sample, you can expect the sample data, the mean from the sample, to be a good estimator for the entire population's average. So we're talking about how range is a bad number. I'm not going to take a sample range and say, oh, that's probably the range for the whole group. It's not going to work well. It's not good. Range is a terrible thing to use a sample to try and figure out what the whole group is like. That's the idea. But if you take the sample average, if you look at an average from a sample, that is actually a good thing to try and figure out what the entire group's average is like. So numbers like this are important, values like this, statistics where you can look at the sample and say, okay, based on the sample results, I can make a good guess about the entire population. So that's our idea. We're going to select a group, and then we're going to look at their sample mean, their average for the sample. And then if we look at a bunch of different sample means, we can make a nice normal distribution and see that the average of those is the mean of the entire population. So that means we can expect the mean of a large enough sample. It doesn't have to be large enough. I should say that right here. It doesn't have to be large enough. If all your samples are like size 2 or 3 or 4, they might not be big enough, especially depending on the data you started with. So you like to have big enough samples. If you have a big enough sample, then we can expect the mean of that large enough sample to be close to the population mean. So it's allowed because of this fact up here. We can expect the average of a large enough sample to be close to the population's average. So if I wanted to go figure out, the average height of Americans, I can actually take a large enough sample size. If I have a big enough sample, I can take the average of that sample and say, yeah, that value is going to be pretty close to the average American's height. That's something that's a legitimate expectation to have. We call the distribution of these sample means, all these little sample means, this distribution we call it the sampling distribution. That's just a fancy name for the chart distribution made of all the averages from all our different samples. So the distribution of sample means is called the sampling distribution. And we use mu sub x bar to mean the average of the sampling distribution. So it's going to be the value that's going to be in the middle here as well, the average of all these guys. And we use sigma sub x bar for the standard deviation of the sampling distribution. So it'll be the spread of this chart. So mu sub x bar is going to be the mean of the sample means, and sigma x bar sub x bar is the standard deviation of the sample means. What these are going to mean for us is if we're looking at a set of values and not just one value, in the last two sections we would look at just one specific value. I'd give you one number. We use it for z-scores and stuff like that. Here we're going to actually look at a collection of values. We're going to have a sample set. So sample set's not going to just be one person's height, it's going to be 10 people's heights. Well, when we're working in that case, we're working with multiple people with a sample, then we're going to be using these values. We're going to be using the mean for the samples and the standard deviation for the samples, not just the mean for the entire group and the standard deviation for the entire group, because we're not looking at everybody individual. So, when working with samples, which means that the sample size is going to be n, is going to be bigger than 1. There's more than one person, so n is bigger than 1. We have 2, 3, 4, 5 people. Then we use the mean of the x bars, the mean of the samples, and the sigma of the x-bars, the standard deviation of the samples. That's what we're using when we're with samples. And the big thing is samples that have more than one person. And we'll kind of see that as we go to the problem examples. You'll see the distinction between when you have just one person or when you have a sample and you're working with more than one person. But before we get too much to actually doing the actual math for this section, we're still going to talk a little bit more, trying to get this idea of what we're dealing with. So we're going to show an example in this case where, and this isn't something maybe you'll do in the homework, but kind of an idea to maybe help you understand what we're talking about right now. How we can look at samples of size 2. So we know this is n is bigger than 1. We're looking at samples of size 2 and compare the population mean and the average of the sample means. And we want to show how that those are actually related. So the population mean, that's the average for the entire population, and the sample mean, the average for the sample means. And we're going to do it for this data set. So that's the data set we're working with. So we got 76, 78, 80, and 84. That's the data set. So first, if I just wanted to find the mean of this set, if I just wanted to find the average of this set, remember that to do that, we're just going to take all the values, 76 plus 78 plus 80 plus 84, add them all up and divide by how many there are. Well, there's 4 values, right? So divide by 4. And that would give us our mean for the entire population. So if I want to find the mean and I have all the values, you know, just add them all up. Of course, this is a small data set, so in real life you wouldn't have this. It'd be a lot harder. We add them all up, divide by how many there are, so there's only 4 numbers in the data set, and we see that this is the population average. This is the mean for the entire population. For all the values we have, it's a small population, that's why it's easy to do. But if we compare this with the mean of samples of size 2, we'll see that there's a good, strong comparison there. So we're going to look at samples. Now, these are all samples you could get. So you could pick, if I pick 2, and I'm going to allow repetition because then we can avoid that whole dependence with the probabilities. So we'll look at all the possible samples, even if you include the same thing twice. First up, let's look at the average of each sample. So if this first sample I picked 76 both times, so what's the average? Well, the average in this case would be 76, because the average of 76 plus 76 divided by 2 is 76. These ones, I got 76, 78, or 78, 76. Those would be 2 different samples. Both of these are going to have an average of 77, because that's halfway between those two. 76 is 80, and 80, 76, and 78, 78 all have the same average of 78, because if you add those up and divide by 2, you get 78, or the same thing there. I have 78 and 80, 80, 78, 76, 84. All these ones have an average of, or sorry, these two, just these two, not the third one. These two have an average of 79. Next set here, I have an average of 80. Let's have an average of 80. This set here, what is it? I think it's 81. These ones have an average of 81. These ones have an average of 82, and this one has an average of 84. Okay, so we found the means. These are the averages for all these sets. Now we want to find the means of all these sample means. So we're looking to find the means of all the sample means. And we're going to do that using the expected value calculation. So we saw this expected value calculation before where we find the values, these would be our values, and then the probabilities of those values, and then we multiplied those and then added them all up. So first we want to find the probabilities. Well, notice that there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 possible values. So there's, or sets of 2, so 16 total samples. So to find the probability of each of these, I just take, how many options work out of that 16. So the first one would be, 1 out of 16, which is 0.0625. So 0.0625. Here I have 2 out of 16. So 2 out of 16 is going to be 0.125. That's going to work for a few of them, right? Because all of those that have 2 options are 0.125. 125, and I guess this last one would also be a 0.0625. And then I have one that are some that are 3 out of 16. That's 0.1875. So 0.1875. Okay. Now we're going to take those values times their probabilities and get this calculation. So I'm going to just multiply those out. So the first one I do 76 times 0.0625. And again, you're not going to have to do this calculation on the homework, but I just want to illustrate this idea about the average of these samples versus the average for the whole population. Next one, 77 times 0.125 is 9.625. 78 times 0.1875 is 14.625. 79 times 0.125 is 9.875. 80 times 0.1875 is 15. 81 times 0.125 is 10.125. 82 times 0.125 is 10.25. And 84 times 0.0625 is 5.25. Okay, now if I total these up, add them all up, that will give me the expected value, which is another way of saying the mean for all these samples. I'm just going to add these numbers up. A little bit of typing in. 4.75, 10.625, 14.625, 9.875, 15, 10.125, 10.25, 5.25. Okay, hopefully I got them all typed in there. I should get 79.5, which is actually what I did get. So I got it typed in there correctly. You can't see that. 79.5 was the average. So what this shows us is that the average for the entire group, this is the population mean. The population average was 79.5. This one out here is the mean of the samples, right? We found the averages for the samples, and then we averaged those, and we got the exact same average. And so this is what we were saying on the last page, that when you make that distribution from all these little sample means, the averages from each sample, the average in the middle here is actually going to be the same as the population average. So mu is going to be equal to mu sub x bar. The average of these samples is the same as the average of the entire population of data. So that's what is important, because then if I pick a sample at random of 2, it's going to be somewhat close. It's going to be somewhat close to my average of 79.5. You notice that the furthest I can get from a sample is either to 84 or 76. And either of those, they're still fairly close to 79.5. And those are the least likely ones, right? These are the least likely ones. Most of them, have 2 or 3, are going to be even closer to 79.5. So again, this is all just to illustrate and really bring up the point that when you take a sample and find its average, you can expect that result to be close to the actual average for the entire population. Now, you can't expect it to be exactly right every time, right? Every time I pick a sample of 2, I'm not going to get 79.5. In fact, none of these gave me 79.5 as the average. But a lot of them are pretty close, right? 78, 79, 80, 81. Those are all really close to 79.5. So if I'm trying to estimate and figure out what the average for the entire population is for all my values, I can take a sample of it, look at that average, and expect to get a number close to my real average. And this is why someone can go out there and they can take the heights of 40, 50, maybe 100 high school boys, and then they can say that they have a good estimate for what the height of all high school boys is, even though they didn't go out there and measure all the high school boys. Now, they don't know that they got the exact right answer, but they have a good estimate. They have a number that's close to it. And they know that because of this property, this principle, that the average of all samples is going to be close to the same average as the average for the entire population. Okay. Now, I've been talking about how some numbers are good, some aren't. So let's talk about the word we use for those and what those are. So the ones that are good are called unbiased. They're not biased, and being not biased is a good thing. It means that you're not going to be messed up one way or the other. You're going to work well. So we call statistics, so that's the result we get from a sample set of data. Unbiased, important word, if it targets the population value. We call parameters, if they're the population, we call them statistics from the sample. So again, that's saying that the sampling distribution of the statistic has a mean that's equal to the population parameter, which probably isn't the best way to say it. Maybe a better way to say it is that the sample values are going to probably be close to the population value. And there's 3 big ones right here. 3 big ones are proportion, mean, and variance. All of those are unbiased or good estimates. So proportion, that's a percentage. So like what percentage of people group are of high school degrees, or what percentage of people have caught an illness. That's a proportion. And the proportion from a sample is a good estimate for the proportion for the entire population. Mean, we just talked about in the last page, is a good example. Mean is a good estimate for the entire population's mean. And variance also works. So if you look at variance, remember we said we're not going to do a lot of time with variance, and we won't, but it is actually a good unbiased estimator. It is something that people do use. And that's why if you go into more advanced statistics, they will use a lot of variance because it is a nice unbiased estimator. But variance will estimate the variance of the entire population. So you take the sample, your one sample of data, and you can use that variance to estimate the variance of the spread. So proportion, it's going to be percentage, what part of the group has a property. Mean, what is the average value for the group. And then variance is a measure of spread again. So it's like a spread value measure. Things that don't have, that are not unbiased, things that are biased, which is not what we want. Statistics that are biased, they do not target the population parameter, would be things like median, range, and standard deviation. These are not. So we already talked about range is terrible, right? Because you take a range from a small group, a sample, and if you just get values that are not very spread out, then you're not going to get a range anywhere near the range for the entire population. So when you talk about range for the entire population, you're talking from the smallest number to the possible number all the way to the biggest. If you talk about range of just your sample, well, you don't have a lot of those big numbers or small numbers. You just have whatever is in your sample. So range is terrible. Median is also not very good. Remember, median is the middle number. Well, again, if you pick a sample from a large set, you might miss out on a lot of large numbers or a lot of small numbers. Median might get messed up, so it might not be very good. So median is not good. Standard deviation is not good, but we'll actually give it a pass. So standard deviation is biased, and so it does get messed up a little bit by samples versus populations. But it's small bias, so we still use it, even though it's not the best. So we actually still use standard deviation. So we'll actually do that throughout the rest of the semester. We want to estimate the population standard deviation, the spread of all the data. That's the population standard deviation. We will take a sample set of data and we'll try and use that as an estimate for the population. It will make the math harder, and you'll see that when we get to later sections. You'll see that if we don't know the population standard deviation, we have to use the sample standard deviation. It'll make life harder because it'll make math harder because it's not truly biased, unbiased. So again, it's better if they're unbiased. So these are good, and these are not so good. These biased ones are not so good. They're not good estimators. So again, if we can, we prefer to work with the good ones, but if we do have to, sometimes we'll have to work with stuff like standard deviation, then we'll deal with them when we have to. Probably we'll never use range or median because they are not good, and so we'll just avoid those. Okay, so one of the most important things in this section, we've kind of been building up to it so far, is what we call the central limit theorem. We stated that the sampling distribution of the sample means was normal for large enough sample size. Now, I've used that word large enough, but I never defined what large enough is. Well, here is the central limit theorem where it tells us what large enough means. So if a sample of size n, where n is bigger than 30, so that's actually the magic number right there. 30 is your magic number. If your sample is bigger than 30, then it's big enough, always. Any sample over 30 is big enough. Then you can actually estimate the mean of the population is going to be the same as the mean of your samples, and the standard deviation of your samples will be the same as the population standard deviation divided by the square root of n. Now, where is this going on? Well, what happens here is the bigger your sample is, the less variation you're going to end up having. Because if you have a big sample, you have so many people in your sample, you're going to be closer to the true average, the actual average standard deviation. So what happens is the spread decreases the bigger your sample gets. So the variation decreases as sample size increases, which makes sense, right? Because if you think about, if your sample size gets bigger, you're getting closer and closer to taking like the whole group as your sample. And so if you take the whole group, well, of course, then your average for your sample is going to be right on the average for the whole group because of the same thing. So the bigger your sample gets, the closer you get to the true average for the entire population. And so what happens is the variation, the spread of your data will decrease. You'll get, it won't be as spread out as you get bigger and bigger sample size. So the sample average, the standard deviation of the averages of the sample means is equal to the standard deviation of the entire group divided by how big your sample size is. This one, square root of n, n's your sample size. So the bigger your n gets, the bigger the number on bottom gets, the smaller this quantity gets, right? Because the standard deviation will be decreasing as n gets bigger. Because when you divide by a bigger number, you get a smaller result. That's what that sign is. Here, this one, it's just right off the same, right? There's no division or anything happening. So it's going to say that the average of your samples is going to be the same as the average of the entire population. That's what that one says. And this is as long as you have sample size n, where n is bigger than 30. If you have a sample size less than 30, then it's going to be a little more complicated. We'll talk more about that as we go, but that's the idea. So this is going to be the thing that makes this section really different, especially when we hit the math. Because in previous sections, we weren't working with samples, we were just working with one individual. So we didn't have to worry about doing this dividing by n, because if you have one person, well, n is just 1. The square root of 1 is 1, and dividing by 1 doesn't change anything. But now, in this section, we're going to start working with samples more than just one. We're going to have a group of people, and so we'll actually have to tweak the standard deviation is what we'll see. We'll see the standard deviation ends up decreasing whenever our sample is more than just one. You'll see that in practice. It's not that complicated, but once we get to, that's the big ideas, the sample size. Here, this is just a kind of a graph showing, a picture showing why sample size 30 is good enough. So what happens is, if you start off with a chart looking like one of these three, so if your data that you're working with looks like a nice normal distribution, or maybe it's not normal, it's like a curve, or maybe it's uniform. If your data looks like that, well, as you pick bigger and bigger sample sizes, so like sample size 2, sample size 10, and then this one sample size 30, what you'll notice is that the distribution for your sample means, gets more and more normal the bigger your sample size gets. Like, it starts off normal, it's always going to be normal. So you see all three of these are normal. But if it starts off not normal, well, at first it won't be normal because it's not big enough, right? This is only sample size 2. But as it gets bigger, you'll notice it gets closer and eventually closer to being normal. And this one's not quite normal, but it's so close to being normal, you can kind of treat it as normal. It's not really cheating, but it's saying that if it's big enough, sample size of 30, you can actually treat this like a normal distribution because it's so close to normal distribution. Same thing over here. Again, it starts off uniform, not normal at all. Sample size 2, it's still not normal because it's too much of a peak. As you get 10, 30, it's definitely getting more and more normal. So again, if the original population is not normal, if it's one of these two where it's not normal to start with, and you're less than 30, then it's not going to work out. It's not going to be normal. In those cases, we're going to leave that for the advanced classes because you have to use more advanced techniques. So we'll basically only deal with problems where it's normal to start with, so it's always normal, or the sample size is so big that it looks normal. So that's what we're looking for, is that sample size 30, which is perfect, or these ones that are already normal. So this one's normal to start with, and these ones, n is 30, and so that's where we're big enough. You technically n has to be bigger than 30, but that's close enough. That's what we're looking for. So again, so what we know, central limit theorem says that the mean of all the sample means, so the mean of all the averages, we took all the different samples and the average of those, is the same as the population mean. So the sample average equals the population average. So the average of all the different samples you could take, all their means, is going to equal the whole population's average. And that the sample mean, sample standard deviation is equal to the population standard deviation divided by the square root of n, where n is the sample size. So the sample, the standard deviation for all the samples, is going to be the population standard deviation divided by the square root of the sample size. That's what that's telling us. Okay, let's see it in action now. Now we're actually going to get to the math. So this is what you're going to kind of see when you do problems. This is the idea. So let's show an example. A parent is curious about how much time kids play video games. According to a study by the Bureau of Statistics, the daily time for a teenager plays video games is normally distributed with a mean of 4 hours. So they have a mean of 4 hours as their normal distribution, and a standard deviation of 1.5 hours. So that's going to be, in this case, our population mean. So they give us the mean. This is for everybody. So the population mean is 4 hours, and population standard deviation. So the standard deviation for everybody is 1.5 hours. They want to know, what is the probability a randomly chosen teen will play less than 3.5 hours daily? So we're looking for the probability percentage less than 3.5. So if I draw a little normal distribution here, the middle is going to be my 4, right? That's the middle. This is the average. Mean goes in the middle, that's 4. They're looking for 3.5 or less, right? So we're looking for less. They want to know what this area is. That's what they're looking for. Now, if we look at just the probability of a random, and that's actually an important thing right here. They say probability of a random. This is for just one person, so one teen. So one teenager. In this case, because we're looking at a sample of size 1, we don't have to worry about like the whole averages or the samples. You know, we're not taking a sample of more than one. We're just doing one teen. In this case, we're just going to find the area the way we've been doing in the last two sections. Since we're looking for area, we'll use that normal CDF. We'll put our lower bound, which here we want everything less than 3.5, so we don't have a limit. So we'll do that negative 10 to the 99th. That's just a really small number. And then we'll say our upper bound would be 3.5. That's where we want to hit, 3.5. Oops, I forgot the mean. The mean in this case is 4. Don't do that yet. I want 4. And the standard deviation, which is 1.5. So that should look the same as what we've been doing in the last two sections, right? Where we're finding the normal CDF, especially the last section where the mean is not always 0. So we have the mean, we have the standard deviation. We didn't change anything because we're looking at just one teen, just one person. And that's why it just looks the same as last time. And you're working like that, and we're working with just one person. So we do sample distribution, normal CDF. Again, negative 10 to the 99th. Upper is going to be 3.5. My mean is 4. My standard deviation is 1.5. And that gives me a value. So my value for this one is 0.3694, or about 36.94%. So there's a 36% chance, if you just pick one teen by themselves, that their average time playing is less than 3.5 hours. Okay, this is for one teen. Now, what if, instead of looking at just one kid, what if we say we have a group of 18 teens and the time they play is less than 3.5 hours? So the difference here is now I'm not just looking at one person, I'm looking at a group of people. So I don't get to use the standard deviation as is, because remember, the bigger your group gets, the smaller your standard deviation gets. We are going to still use the mean of 4, because that's still our mean. That doesn't change, right? Because we said that the mean for the population is always going to be the same for the mean for the sample standard deviations. But to find the standard deviation, we're going to have to divide by square root of n. So for the second part, when we have 18 teens, our sample n is 18, then we're going to use the same mean. The mean for the x bars is the same, still 4, but to find the standard deviation for the samples, we take the previous standard deviation, that 1.5, and we divide it by square root of n, which in this case is 18. So again, the standard deviation of the sample means is going to be the standard deviation divided by square root of n. That's where we're doing that. So as soon as you get more than one person, you get a group of 18 people, you got to change the standard deviation. So if we type this in a calculator, we're going to decimal from here. 1.5 divided by second square root 18. We see that the standard deviation now, instead of being 1.5, is all the way down to 0.354 if you want to round it. So we'll say this becomes 0.354. So that's much smaller than our original standard deviation. Because we have 18 people, not just the original 1, we have 18 people, the standard deviation has dropped quite a bit. It's gone all the way from 1.5 down to 0.3. If we had 20, 30, 40 people, we'd see that standard deviation get smaller and smaller and smaller. The closer the further you get, the closer you get to the total population, the smaller that standard deviation is going to get. So we're going to do the same normal CDF, but the difference here is we're going to have a different standard deviation. So it's still going to be normal CDF, because we're still looking at the percent less than 3.5, so we're still doing this area down here. So we're still going to have negative 10 to 99th, because we want to go to left forever. 3.5 is still going to be the top. The mean is still 4, right? That did not change. The mean is still 4. But the standard deviation is what changed. That's the important part. This became 0.354. It's smaller now because we have a group of 18 students. That's the important part. Having that group decreases the standard deviation. Otherwise, this is going to be a lot like what we did last section, right? There's not a big change. The only difference is that change in the standard deviation because we have a sample of more than one person. I'm going to type that in my calculator, so I'm going to do my second distribution, normal CDF. It's negative 10 to the 99th, 3.5. I don't really have to change these because I already do the same in there, but I'm going to type them all anyways. And then the big difference is my standard deviation is 0.354. So I've decreased the standard deviation. There's less spread because I have a big sample. So I hit enter on that, and you'll see I get a much smaller percentage now. So I get 0.07, 89, I guess if I go enough decimals, or 7.89% if you turn it into percent. And you can see that's a lot smaller percent, 7.89% versus 36%. And the difference is, when you have 18 people in the group, what's the likelihood that the group is going to be way under average? Because this is 3.5 hours instead of 4 hours. If average is 4 hours, my group is going to be probably a lot closer to 4 hours. Because when I have a group of people, it kind of balances out, right? When you only have one person, it's possible they might just be that one kid that plays a lot less, does a lot less hours of video games. But if you have a group of 18 kids, well, yeah, you might have 1 or 2 kids that play less, but you're going to also have some kids that play more. And so it's going to balance out, and you're going to be closer to the average. You're going to be closer to the average of 4. So trying to find a group that's actually all less than 3.5, in the lower range, that's going to be a lot less likely because you have a big group instead of just one person. So the bigger your group gets, the closer you're going to be to average, the less likely that you're going to be below average, or falling to be above average. You're going to be closer to the middle because there's less spread. Remember, standard deviation is spread, so less spread puts you closer to the middle. So you're going to be right in the middle. And that's why this gets to be smaller. This area here is going to be smaller because more people are going to be in the middle. The spread, remember, as the spread decreases, the chart gets really tall in the middle, and it doesn't go out as far to the left and right. And so that's what that's telling us. So more people, less standard deviation, tends to make for a smaller percentage than when we did it with only one person. So there was more spread because we didn't decrease the spread. Okay, let's do a couple more. But again, the big thing is noting that 18 teams. When you get to the test, the really way you can tell the difference between questions from section 6.3, 6.4, and questions from 6.2 is that when they say there's a group of people you're studying. It's not just one person. We're not just doing the chances for one person. We're doing the chances for a group of people. That's going to be the big defining difference. Okay, do 2 primary examples, and we're done with this section. Okay, so an engineer is designing a car seat for weights between 30 to 36 pounds. So it wants to be between 30 to 36 pounds. In the U.S., toddlers have a mean weight of 32 pounds. So that's the average weight for all toddlers. So that's going to be a mu, right? That's the population average. So the population average is 32 pounds. There's a standard deviation of 6 pounds. So for all those toddlers, standard deviation is 6 pounds. So that's the standard deviation for the entire population. And a sample of 25 toddlers. Oh, that's the important right there. 25 toddlers tells me that now my sample size is 25. And since my sample is 25, I'm going to have to tweak that standard deviation. It's going to get smaller because it's not going to stay 6 because we have a group. What are the chances the mean weight will fall between 30 and 36? We want to find the probability that it's going to be between this range. So I draw a little chart, I draw a little distribution. I know that my mean is going to be in the middle, so that's going to be my 32. I'm looking for it to be between 30 and 36. I'm looking for the region here. What's this area? And again, to do these areas, if we have the values, we're going to use normal CDF, just like before. Lower bound in this case would be 30. That's the bottom. We want between 30 and 36 at the bottom, 30. Top is going to be 36. The mean, remember for a sample, the mean is always the same. So the mean of the sample averages, the mean of the samples, is the same as the mean for the whole population. So that just stays 32. No changes there. But the the standard deviation for the samples Remember, to do that one, we have to take the standard deviation and divide it by square root of n. So because we're dealing with a sample of 25, right, 25 people, we're going to take this standard deviation of 6 and divide it by the square root of 25. So I think that's 6 divided by 5, which is like 1.2. I can double check by typing my calculator. 6 divided by the square root of 25 is 1.2. I was right. Okay, I could have just gone with that, but better safe than sorry. So 1.2 is my standard deviation for this one. Because I have 25 people in this group, instead of a whole standard deviation of 6, they only have a standard deviation of 1.2. Because when you have a big group like that, 25 people, you're going to expect them to be closer to that average of 32. So their standard deviation, the spread, is going to be less. And so then the value, the percentage that's going to give you this region, in this case, because you're close to the middle and stuff, it's actually going to end up with a lot bigger percentage, I think, because now we're looking at the right in the middle. We weren't looking at the ends. So the stuff is going to sucked up into the middle, and so since we want to include this middle, we're going to get a big percentage right now in this case. All right, let's type that in the calculator and see what we get. So second distribution is just that normal CDF option. Lower bound in this case is 30. Upper bound is 36. The mean for the toddlers was 32. And because we tweaked that standard deviation to account for the 25 people in the sample, we got 1.2 for the standard deviation. So that gives us 0.9518, so like 95%. So this is really big, like I said, because we sucked everything in the middle. We decreased the standard deviation, so everything got sucked up into the middle, because we should decrease the spread when we picked a big sample group. If we picked like 30 or 40, this would actually go even higher, because the bigger your sample, the more everything gets sucked closer into the middle. The second part of this one actually asks, what are the chances that one toddler will have a weight between 30 and 36? And so that's the big difference, right? When they're talking a group of toddlers or a single toddler. When we do one toddler, then we don't change anything, right? We don't have to change the standard deviation to get the tweaked standard deviation. We're just going to use the regular mean and the regular standard deviation in this case. We're going to use the regular 32 for the mean, regular standard deviation of 6, because we only have one person. And so if you have a group, you have to tweak the standard deviation, but if you only have one person, you just leave it as it is. So in this case, I'd still do normal CDF. The low value would still be 30, and the high value would still be 36. So 30 and 36. Mean is 32, and this time the standard deviation would be 6, because we don't have 25 people. If I divide 6 by the square root of 1, you'll notice it just stays 6. So when there's only one person, you don't change the standard deviation. And that's the big difference. Okay, let's try this one. So we do second distribution, normal CDF, still 30, still 36, still 32. All those stay the same, but now it's 6 for standard deviation because we only have one person. And this time I only get 0.3781 or 37.81%. So you see this decreased quite a bit, because when you have a bigger standard deviation, everything's more spread out. There's not as much in this real area anymore. So that's why this is going to get to be a lot less, because everything's spread out. When you only have one person, there's a lot more likelihood that they might be away from the middle. So values that are beyond 30 or beyond 36, since you only have one person, those could happen. But when you have a group of 25 and you look at their average, you kind of cluster everything in the middle. And that's the big difference. That's why this one was so big at 95%. The other one was so small at 37%. It's all about a group. Where you get a bigger group, you get closer to the middle. In this case, that makes you bigger because we're looking for the middle area. Or if you have a single person, you spread out, so you have less in the middle. The difference between looking at the middle in this problem versus the previous problem, where we were looking at the end and everything was moved in the middle. So the middle one, the one where everybody got clustered together, ended up being smaller because we were looking for the end, not the middle. Okay, let's try one more example. This one I want to definitely help you out because there's kind of some questions like this in the homework that can tend to trip people up a little bit. So let's look at this passenger jet problem. Okay, a passenger jet is carrying 45 people. Oh, there you go. That looks like a sample size to me. 45 people, so that's probably going to be our N, right? N is 45. It has a maximum weight capacity of 7,425 pounds. The average person weighs 166 pounds, and there's a standard deviation, so standard deviation of 30 pounds. What are the chances the jet is overloaded. Should the pilot take action to correct for an overloaded aircraft? So this one gets a little weird because it's like they give us the weight of the aircraft, they give us the average weight of a person, so we can kind of see that the average weight of a person is 166, and then the weight capacity is 7,425 pounds. But they don't tell us like what value to use from this. Well, the trick here is noticing that the passenger jet has 45 people and a total capacity of 7,425 pounds. We actually can kind of figure out what weight they're looking for by comparing those and noticing that if we take the 7,425 pounds that the jet can carry, divided amongst the 45 people the jet is carrying, then we can kind of look at what our limit is for the weights of the people. So that's the trick on this one, is to notice that they tell you how many people are on the plane, they tell you how much weight the plane can carry. So if you divide those, you can find out that 165 pounds is basically the limit. If the average weight of the people on the plane is 165 pounds or more, then they're in trouble, right? Because that's the maximum weight capacity. They don't want to be at maximum, they want to be below maximum. So what are the chances that they're overloaded? Well, they're looking in this case, chances that they're overloaded is going to be the chances that it's greater than 165. Because if the average weight is more than 165, then the jet's overloaded, right? That doesn't mean everybody on the plane is going to be over 165 pounds. There might be some 100 pounds, 120 pounds, but overall, on average, the weight is over 165 pounds. So there's some people, for each 100-pound person, there's a 200-300-pound person. And overall, average weight ends up being more than 165. So this is the maximum average weight. You know, yes, I know the real average weight of people is 166. That's the population average, right? So the population average is 166 with a standard deviation of 30 pounds. But we have to look at the chances, what's the probability that the average weight for this group is above 165. So if I draw the normal distribution, I put 166 would be in the middle, and then 165 would be on this side. Oh, 65. 65. And we're looking for the average weight being above 165. If they're below 165, they're safe, right? We're good. But if they're above 165, we're in trouble. So we're actually looking for this area. That's going to be our probability area. The probability for this region, this whole region here, would be 165 and above. Okay, so we're looking for 165 and up. So we're going to do a normal CDF, where the lower limit's going to be 165. The upper limit's going to be, well, anything above 165 counts. So we'll do the 10 to the 99th positive because we're going up. The mean, well, the average weight we know for this is actually 166, right? 166. And then the standard deviation, well, don't use 30 because remember, we actually have a sample set, right? We have 45 people. That's just one person on the plane. We have 45 people on the plane. So we actually have to take that standard deviation and turn it into the sample average standard deviation. So we have to take it and divide it by the square root of the sample size. So I take that 30 standard deviation for one person and divide it by the square root of 45 because there's 45 passengers. Because we're looking at when you have more people, not just one person, it changes the standard deviation. It always decreases it. So we have 45 people on this plane. Standard deviation is going to decrease. So we get 30 divided by a second square root of 45. And that's actually our standard deviation. And notice it's a lot smaller now. So our standard deviation for this one is 4.47. Okay, so that's what we're going to use for the value, 4.47, not the 30 that we had before. Okay, let's see what that gives us. So we can do normal CDF, so second distribution, normal CDF. The lower limit is 165, because again, that's you know, anything below that's okay. So we're looking for the bad region, so 165 or bigger. The upper region is 10 to the 99th. I'm just using a really big number, right? 10 to the 99th is just really big, so we get all our values. And then the average weight is 166, and the standard deviation for this group is going to be 4.47. Again, because we had 45 people, and we took our original standard deviation and tweaked it to get the new standard deviation based on having 45 people. All right, put that in there, and we get 0.5885, or 58.85%. So I don't know about you, but if I'm the captain of this plane I look at that and I say, oh, I have better than even odds, right? Better than 50% odds. I have almost 60% odds that the plane is overloaded. So at this point, I start doing things to fix it, right? And this is why sometimes planes will not have your luggage on them when they get to the destination, because they might be so full, so booked, they say, oh, to account for all the weight of the passengers, we actually have to reduce our weight load, and they'll actually take baggage off the plane, and they'll put it on a different plane that actually has less people on it. And that's why that happens sometimes. That's sometimes you get to your destination and it doesn't have you don't have all your baggage there because they took it off, put it on a different plane, so that plane could bring it to the destination later on. And they'll do that. That's one of the normal adjustments they make. If the plane gets too loaded, there's too many people on it, then they stop and they adjust the weight to make sure that they are not overweight. They do that calculation. So, okay. So again, the big thing here is we're shifting to looking at these probabilities, percentages when we have a group of people. So not just one person, but we had a group. We had a group of 45 people. And really what it boils down to is, you keep the same mean, but your standard deviation gets tweaked based on how big your sample group is. So that's the big change we'll see. Okay, that's it for this one. So I'll see you on the next set.